Okay, okay, great. We're talking with Shriram Krishnamurthy, who is an expert in many things: software engineering, formal verification. He's done some work on a system called FlowLog, which allows for reasoning about SDN control programs. And we're going to talk about formal verification and control as it pertains to SDN. So, thanks for the time, Shriram.
Real pleasure, Nick. Thanks a lot.
Cool. So I guess FlowLog is actually one of the first things I think we've seen as far as like looking at reasoning about SDN control programs and sort of looking at trying to basically design a language or an interface that would allow SDN control programs to be verified. I'm wondering how you sort of designed this set of abstractions that FlowLog supports. Like it's based on data log. I think also people probably don't know too much about it, so I'm going to tell them, like, give them.
Yeah, sure. I can talk a little bit
Kind
about
of like arrive at the design for FlowLog.
Right. I think two different things came together. So one is in the past we did a bunch of work on verifying and reasoning about um, like Cisco iOS programs, via Cisco iOS policies and access control policies and things like that. We had a system called Margrave that we still use for doing this. So we were informed by thinking about rule-based systems in general. And one guideline for us was it looks like when you look at a lot of real-world policy languages, a lot of them tend to be, in some sense, rule-based, and people seem to work with these pretty well. Another example is something that's not a policy language, but is still kind of rule-based, is SQL. So one set of inspiration for us was really these kinds of rule-based policy languages and SQL, and even syntactically we tried to draw some inspiration from things like SQL because we wanted to make this look familiar. So even though data log is the logic that's underneath, to me that's kind of like saying, well, underneath SQL is relational logic, but there's a language on top of it that tries to provide a rule-based interface that people can work with much more easily. So that was a major inspiration. But the other really interesting thing, I think the sort of the novelty in FlowLog is that it's what we call tierless. And so this is kind of important to us because there's an analogy here to the kind of three-tier architecture you use on the web, right? There's some backing store that's a database tier. Then there's some control tier, which is maybe your Java servlet kind of thing. And then there's client code, which is maybe in JavaScript. Right? And something analogous seems to happen in SDNs where you have some backing store, there's some persistent data you need to store. Then there's the control plane, and then there's the data plane. And in the data plane, you have these, these rules, these SDN open flow rules or whatever. And whether or not you want to be writing JavaScript by hand. Right? So the analogy breaks down a little bit, but even more so than that you would really like to not be writing these by hand. There's no UI involved. There's no analog to CSS. You would really like to not look at this if you can help it, except in some maybe performance tuning aspects or something. So FlowLog's goal is to be this tierless language. So the way we accommodate that is the back end is, that's just, we've anyway got a relational store. So that maps very nicely to what we want. And then the client side is basically we compile these rules down so that the programmer thinks they're working in this one tier and the other two tiers are generated by a compiler. So that's the other big design principle. So one big design principle is let's draw inspiration from rule-based languages and SQL and so on. The other inspiration is let's be tierless and see how that works out. And the right way to think about it is an experiment. And a few years from now, we might say, it wasn't so great, but it's worth doing for now.
Was the decision to sort of focus on rule-based, like a rule-based abstraction? Was it like we want to design something we can verify, or was it that like, oh, people kind of know SQL, or they're familiar with that, so let's kind of go?
It was actually, so that's a great question because we were trying to find the sweet spot between those two things. Right? The sweet spot between what do we think people would be willing to program in and might find familiar, but at the same time, what can we verify, and in particular, what can we throw pretty heavyweight verification at? Because people will also program in Python happily, but it's really hard to verify Python, especially if you want to do certain kinds of verification. And FlowLog is designed from the ground up. Again, that's another aspect of the experiment, is can we sort of co-design a language and its verification support together? And so, unlike other places other projects where you add as much expressiveness as possible and then try to claw back verification, we're trying to be a little more conservative and use verification support as a design principle to figure out when we can add things and in what form we should add things. So that's the other part of the FlowLog experiment.
Mhm, mhm. It's interesting, actually, kind of like talked about ease of programming and familiarity, and I kind of imagine like network operators. I mean, I'm imagining now, so let's see, but that they're, perhaps more comfortable with something like SQL than like a general purpose programming language. I mean, I know sort of as a as a matter of experience teaching this course that there are many network operators who certainly aren't programmers. Many of them who've kind of never seen programming languages. So I think there's a real challenge in kind of like designing something that an operator could use that they could even understand without like a huge learning curve. And I mean, is that something that you're concerned about? Is that, I mean, it seems like something we need to be concerned about, but is that
That's right.
something you're considering as well?
Yeah, yeah, I think very much. I think you've hit the nail on the head. I mean, there are, and this isn't like, we're not trying to disparage NetOps or anything, right? They're perfectly capable of learning programming, but that's not what they wake up every morning thinking that's what I want to be doing right now. So I think over time, SDNs in particular are going to open up a new generation of NetOps people who are also programmers, software engineers, and so on. Because I mean, one of the beautiful things is SDN has made possible for these people to come in and contribute. But we'll have all kinds of people and people with expertise more at the network level, at the hardware level, and figuring out what kinds of abstractions work well for them, I think, is a worthwhile activity. So one approach is you could think about building domain-specific languages inside some more general thing. And FlowLog you can think of as it's a different kind of domain-specific language. It's just not embedded in some bigger language. Right? Now, one design decision in FlowLog is we really want to be able to reuse code that's already out there. People have already written Python libraries and Java libraries and so on. So we've put a lot of effort so far, not as much as we'd like, when we'd like to do much more, on building a good FFI so that and again, the direct analogies to SQL and calling out to external code from SQL, right? Stored procedures. That's directly inspirational to us. So we have this idea that you can call out to external code and there's some signaling and so on. But yeah, it's very much, it may be this kind of rule-based thing, and if it comes with good tool support as well, might be more attractive.
When you talk about kind of calling out to different
Mhm.
procedures or other things too, it seems like there's a tension between and you've sort of alluded to it already, like, and you talk about it in the paper, like this tension between the wanting to express certain things and being able to verify them, right? Like if
That's
you
right.
pop out to a general purpose programming language, like all bets are off, or in some sense, or most bets are off,
That's
maybe.
right.
But then you get certain
That's
types of
right.
things.
That's right.
So how do you figure out, like, okay, you talked about co-design as well. So where do you kind of draw the line, or how do you figure out like what should go in the language versus like, okay, well we'll use that as like a call out.
Right, right, right. That's exactly. So that's a really interesting design point, and like every one of those things is a question of design. I think for us, we actually chose to start with a minimal core and stretch it out only as much as necessary based on the properties we were trying to verify. So, there's a very simple question like arithmetic, right? Does arithmetic belong in the language? It sounds kind of to a non-theoretician, that sounds like a goofy question. But it actually has a real impact when you start thinking about decidability of things and so on, like what kinds of arithmetic can you support. So we've slowly been incorporating, we're doing some projects where we're actually using FlowLog as a target language. Like we are compiling chunks of iOS into FlowLog, so that we can exploit the FlowLog compiler. So you could take this existing switch you've got, this iOS spec, and you can compile it down, and now you have an SDN testbed on which you can try the same thing that you could do before. Right? So it's like a migration path sort of thing. So there, like clearly you need much richer support for some projects like that. So I think the short version is it's not like we have a hard design principle that always makes decisions for us, but verifiability is definitely the most important criterion, not because it's a sort of golden principle, but because it's the hair shirt we've chosen to wear. Right? That's our deal, and other people are going to make that decision differently.
It seems to me, but I mean, it seems to me like a really good thing to kind of try to focus on. I mean, certainly it's something I've always been interested in as well, and it seems
Right.
like certainly
We've done
from
stuff in this area too, so yeah.
yeah from like hard research problems. I mean, it seems not only very useful but also kind of like a holy grail.
Yeah.
Like, wouldn't it be nice if you could do this? But actually, like, I mean, one of the other things too that kind of comes up is I mean, you've kind of alluded to it already. Like, you start with Cisco iOS, and you're like using FlowLog as a target, and now you got to make some choices about, do you represent everything? And actually, that's another question I have is, um, like what kinds of things can you verify? What kinds of things can't you verify? And then do you think that there are things that like are you finding that you made the right choices, or are you thinking like, okay, actually it would be nice to verify these other kinds of properties like
Right, right.
continuous
That's a great
property?
question. Yeah. One thing we've been weak on so far, and maybe that's just our own strengths and biases showing, is we're not very good at these continuous properties. We've been mostly dealing with discrete properties, mostly dealing with, logical properties. And it'd be really interesting to start asking questions that have like real numbers in them, for instance, right? Talking about volumes and bandwidths and so forth. And then going from there to even richer things like, say, security properties. Actually, security is an interesting question in its own right, as you well know, because some of it falls down under the falls under the logic realm, and some of it is not. And it's sort of security touches on everything. So that's a separate matter. But just in general, there are a lot of continuous type properties that we would like to be able to talk about someday, but it's not been our priority. There's also a really interesting question about where does the network topology fit into all this? Because when you write this tierless program, you write this program that's sort of taking all tiers into account, and it only, if it talks about a particular element, a particular switch, it has an identity for it and it talks about it, then that's relevant. Otherwise, it's not relevant. It doesn't care. That's a compiler's job. But there are interesting questions you'd like to ask, such as bandwidth allocation and so on, where it is really useful to say, hey, this is the specific topology against which I want to talk about this property, and that's something that FlowLog says, we present this as a feature, but it's also kind of a bug, right? FlowLog doesn't really talk about the topology at all. And there will be kinds of properties where we can only verify them once we can also get a network topology, a specific topology. So right now the feature is it's topology independent reasoning, but that's also a bug because when you want to talk about topologies as well. So that and continuous properties, I think they actually kind of go hand in hand, because when you have a topology, you can talk about flows, volumes, all sorts of things like that.
It's really interesting. I mean, because I think like this comes up a lot in other aspects of network management, probably also in software engineering as well. Like when you create abstractions, on the one hand, you kind of like create a convenience for the programmer or the operator or whoever. Like for example, the existence of a sort of virtual topology or just a network as one big switch where you don't have to worry about the topology. But now you want to make an assertion or do some debugging on something where you kind of like need to break the abstraction barrier.
Absolutely. I think also one thing that would happen as sort of the research vision for the FlowLog project is we're going to have these callouts, right, to these moral equivalent of stored procedures, and some of the interesting logic will actually go in there, right? Like constructing a route table, right? Maybe we don't want to be writing that in FlowLog, and maybe that'll come from something else, right? There'll be somebody will have written an awesome thing to do that, and as you know, there are all these projects that do that, and we'd like to just copy those in and stick them in there. And then some of that verification of those properties will actually end up being verification of that chunk of code that FlowLog is referring to, and FlowLog is just kind of passing through whatever it says and isn't getting involved in the middle. So there'll be like a lightweight verification of the FlowLog program saying you didn't mess up the information it provided, and then it becomes a matter of verifying that plugin, basically.
Mm-hmm. Do you think like actually this is a question I've sort of grappled with myself, like because there are other kind of control frameworks like frenetic and pyretic that have these composition operators, and you're sort of talking about also composing modules, and this is something also we've sort of thought of like run into as well, where a lot of these formal verification frameworks are they're well suited for like verifying a particular module. Right? But now you like can verify this module and that module. Now you want to plug them together. Like, are there, good formal verification frameworks for doing that? I mean, one that I've run into, for example, is with finite state machines, right? Like, there's really good like, logics for verifying the properties of like this FSM and that FSM. Now I want to compose them. What happens then?
So in fact, that's interesting, because this is one of the really cool things I think about SDNs, is that they've opened up the possibility of using a lot of the literature that we already have on these kinds of questions. So there's actually a lot that we understand about compositional verification and what kinds of logics compose in what kinds of ways. There's actually a ton of really interesting literature on that. Some of which has made it into tools, some of which is still very much it's understood in theory, but maybe there haven't been as many domains that have called for it, or the tool support is not quite there. But I think we actually understand a lot more than is embodied in the sort of popular tools that you can get right now. So as we learn more about this particular domain and the kinds of properties we want to verify, I think there'll be a lot of people doing a deep dive into the literature, and it's going to be one of these great things, right? There's a paper from 1984 in some conference you haven't heard of that actually solves the problem, and now you just have to implement or 90% of the problem or 95%. I think that stuff that's going to happen for sure. I think one interesting thing that's almost certainly going to happen. I'm actually curious of what you think is there's going to be kind of this operating system level that's sitting on the SDN controller, or this virtualized controller anyway, and then there are going to be a lot of people trying to plug in different features, right? I want to have control over routing, and I want to have control over intrusion detection and some other feature, and then we'll have to talk about how these things interact, because they're all going to want to say something about the packet, right? They'll all want to read the packet, but they're also going to want to write the packet, and then we're going to have fun as they start clashing with each other. And this is a problem we actually know a fair bit about from telephony and other domains like that. In a separate life, I did work on modular verification, these sort of feature-based systems, and several other people have done really neat work in this area. And I think this will become a problem, I'm pretty confident, and then we can bring a lot of this literature to bear and then find what's different in this particular domain.
Yeah, it seems analogous. I mean, it seems like, as you point out, there's kind of like operating system analogies where you have applications that all want to sort of touch the same data or have access to a particular resource like the disk or the network, and you need something to kind of...
Exactly.
In some sense, like, it seems similar. In other cases, it seems like there are going to be an entirely new set of conflicts that arise because you have, these maybe aren't just applications, but they're like, operations teams or
that's right.
Sub-organization. I can imagine like different sub-organizations in an enterprise or a campus, right? Each doing their own thing, or each having their own set of control.
That's right, and I think we actually, again, by analogy, in certain domains like access control and so on, we've understood some things about how they should express even their decisions. Like, we've learned that one useful thing is to think about, even if there's a Boolean valued answer, just a yes/no answer, it's really useful if you have a 3-valued answer that includes like, I don't care, like I don't make decisions in this domain, and that makes it easier to compose and chain these things than if everybody's trying to make a decision about things they have no business making decisions about. So I think we have some principles there that'll get us off the ground. That will then enable us to discover what really doesn't work in this domain.
Yeah. On that note, so you mentioned kind of continuous time properties. Are there other kinds of things that you wish could be verified that like are just kind of tough to express? I mean, it seems like these calling outs of these general purpose programs seems kind of hard in general. But are there other properties do you think would be nice to be able to verify, but just are hard in FlowLog or maybe hard in general?
Right. I mean, I think there's a real long-standing challenge of how do you combine kind of rich temporal verification, like what's the long-term behavior of this program, with rich properties about state. Like, I've got these strong invariants about how this data relates, and as you mentioned, you saw this, you may have seen this in our paper where we talk about if you've got a NAT table, right? There's properties. That's a table, but it's actually a map, and it's a map with certain properties. It's like this injective function, and it has to be preserved, but it also has to be preserved across time. And so you have very rich statements about one particular point in time, and HSA does some of that too, right? But then you also have to talk about its evolution across time. And once you add both space and time, it's just the stuff it's sometimes easy to say, well, it's not that hard to write down the property, but verifying it and actually building tool support and stuff and making it scalable can be really nasty.
Yeah, this I feel is like, I mean, at least from my reading of the current literature, like you mentioned HSA, like, and it seems really like there are a lot of these tools that will say like, I can look at the data plane and tell you like this is going to happen now, right? But like, what about for how long will this be true, as you point out? But like, there are other things, right? Can my control program ever generate data plane state that results in the loop, right?
Absolutely.
Like, is there? I mean, it doesn't seem like there's anything that can kind of solve that at the moment.
Right. I would argue that at those kinds of properties, at least expressible in FlowLog.
Right.
And I mean, the thing is, again, we're going to our version of that property would be a little different because we're just not even talking about low-level data plane behavior, right? We're not talking about what rules are being generated or anything like that. We're just talking at some high level about the system state. So you can say that. Now, would you be able to tractably verify it? That's another question. I mean, you did some work on like verifying BGP and using temporal logic and so on, right? So you know that there's that side of the world, and we chose a slightly different tool suite for various reasons that may or may not be interesting. So getting that combination together is difficult. So at least I would say, argue in FlowLog, you can express the property. Would I be able to verify it effectively? Maybe, maybe not.
Yeah.
And
Actually, that was another question I had for you, like, because I mean, in some of the work we've been doing in SDN controllers, like which you may or may not be familiar with, like we've looked at CTL, I guess as they call it.
Okay.
I'm told they never say computation-free logic, but it's just CTL.
Right.
But I'm not an expert in this at all. Basically, Cole Schlesinger basically, said, "Hey, use that," and we're like, "Okay, good idea."
Good.
But then you've used sort of an entirely different set of things. I noticed, like, Veriflow uses like sort of SAT solving kind of. I mean, what's the space here? I mean, how do you kind of reason about like, I want to verify these kind of sets of properties, and therefore I'm going to use this type of logic or this type of method? I mean, maybe this is a really basic formal method question, but I think most networking people probably don't know.
Okay, so let me see. I'm going to condense about 30 hours of lecture into about 30 seconds. I think the high-level question is, are you most interested in temporal properties? I mean, so the practical answer, okay? Are you most interested in temporal properties, or are you more interested in like rich state invariance or state properties, right? And so things like temporal logic, like CTL, LTL, and so on, are very good at expressing properties about things that have to happen over time. The thing that gives them their decidability properties is the fact that they tend to be pretty weak about what you can say about the structure of a state. In FlowLog, because we have this tierlessness, the whole point is that this one program can talk about the entire state structure. I've got this table here, and I've got this other table, and there are these invariants that I need to have hold between these tables. Like whenever this thing does this, this other thing should never do that. Just imagine you have like n data, you have these lots of tables in your database, and you've got these rich integrity constraints between them, right? And here you're writing a program and you want to essentially ask, like, are these integrity constraints going to hold? Like, is it the case that I'll never end up in a state where this thing ends up saying this, but this other thing says that, and they're supposed to be consistent, and now they become inconsistent, right? So the trick, we played a little bit of a technical trick in FlowLog, which is we focused on the state statements. And so that's why things like SAT solving end up being pretty good at that, because you can take these rich logical specifications, compile them down to SAT, and then some magic happens under the hood, and it's all good for the most part. And sometimes BDDs and things like that are also used for this purpose. But because of some properties, there's actually some pretty rich mathematics in the logic behind FlowLog that let us say there's two different things. One is when we want to talk about properties that are inductive, like I want to say at no time does something happen, well, those are actually pretty good because we don't have to look at all of the paths. We can just talk about the induction step, right? If it's true now, will it be true in the next step? And then by induction, it's always going to be true with some base case assumptions and so on, right? And that lets us sort of break the stranglehold of like, how do we talk about long paths? Because if the induction works, then it works over all time, right? That's one trick. And so that let us talk about temporal properties that were a certain set of temporal properties pretty cheaply without having to go to temporal logic. Okay? The other thing that's happening, the sort of interesting mathematics under FlowLog is when you use things like SAT solvers, there's this problem that comes up that's always brushed under the rug a little bit, which is you need to say something about what the SAT problem is, and there's a finite number of bits there. So you have to say like, well, I want 3 of these things and 5 of those things and 2 of those things. And what if you pick the wrong, what if you pick the wrong number? And it turns out for the logic that sits under FlowLog, in many cases, we have a theorem that says in many cases we can actually compute that bound automatically. So you state the property, and there's this subroutine that goes off and says, can I compute the bound automatically? And if it can, it comes back and says, I've computed the bound, and this is a sufficient bound. And if there's no counterexamples under this bound, there will be no counterexamples. right? So it's this property called completeness. So we can do this in many cases, and especially in this kind of change impact stuff, which we could talk about separately if you want. There we can really compute these bounds. So now it's this much nicer automated feel, right? It's got this automation that you want, but it's actually giving you a pretty powerful theorem. But because we're in the space that we sort of carefully navigate it.
That seems. I mean, it's interesting that you're able to take these sort of things that allow for these reasonings about state and sort of cheat and do some stuff.
Right.
Time. This is exactly the kind of thing where I've noticed, like with CTL, like we can say certain things, like we can say that our controller is in a certain state, right? Like, okay, we're in a state that says, like, this host is not infected, and then okay, well, if this event happens, then I want to basically transition to running this set of policies, right? And now I can make assertions about when you can ever get in that state, or can you ever get out of it, or we'll only reach this state if certain other things are true. But we're at the level of talking about, like, pyretic policies or something, right? Like, okay, I can tell you that I'm going to run a program called drop,
right?
But I can't tell you, like, what drop actually does, right?
Right.
What's in the tables at that point. So I don't know. It seems to me like maybe FlowLog is closing some of this gap, like but certainly as we did some of this work, and then I looked at things like HSA, I was like, man, there's this gap here, because like HSA kind of will tell you, here are the things that are true about forwarding, like given the current data plane state, and then here's something like that will tell you, like, what your control program, like, what states it can get into, but what about, like, bridging the gap between, well, your controller is doing this, and that means, like, the state in your network is doing this, and then I can say, like, run this logic over here to tell me that I could be in this state, and therefore that means I have a loop or not. Like, is that the right way to think about bridging the gap? Or
yeah. So right. So we so as you rightly said, we've got these tricks that let us bridge the gap in certain cases. I think what HSA does is really neat. I mean, these are all like great projects, obviously, right? But the thing with HSA is it's this very sort of instantaneous view of the world, and you'd like to think about how to stretch that into a temporal view. And one of the difficulties you're going to run into is if this data plane is being generated from some arbitrary program, well, now you've got all of arbitrary program reasoning is also coming through the door because you left it open accidentally, right? We know a lot more now about reasoning about programs in certain languages, but again, my group's done some research on, done a lot of work on JavaScript and Python and things like that. So we also know what all the pitfalls there, right? We've got all the snake bits marked out nicely now. I think if you make certain restricted assumptions, if you say, look, I'm going to use this language, but I'm going to assume the following things never happen. And this is kind of the way the game's always played anyway, right? Most Java verification tools don't handle dynamic code loading. They don't handle reflection. They're implicitly already scoped the language down to the same version of the language or something. And we have some knowledge now how to create those sanitized versions of languages like Python as well. And so once we do that, then you could imagine building tools that give you more information about what the step-to-step behavior is going to be. But I think that's one direction to go. That's sort of like working from the bottom up. And in FlowLog, we're sort of starting at the top and working our way down. And saying, look, you never want to actually see the OpenFlow rules. That's obviously a stretch. But if you can be in a situation where you never want to see the actual rules except as generated by a compiler, then hey, we can give you much better verification support. So this is the usual game. You sort of work from both ends, and at some point we'll hopefully meet up in the middle.
That's interesting. I mean, like, as you mentioned, kind of like your experience applying verification, like, to other languages and other settings, kind of like makes me wonder, because, like, coming from the networking side of things, I think, well, my bias is like, well, I've always kind of wanted to be able to do these types of things, and it's like, oh, here's SDN. Oh, okay, now suddenly, as you pointed out, like, okay, here's a whole bag of tricks that we can now go digging through and rummaging through old papers and maybe finding some cool ideas. From the perspective of someone who does formal verification types of things and testing and things like that, what's your view on SDN? Like, is it basically like, oh, we know how to do all this already, and we're just sort of like, we're going to turn the crank on this new domain, or does SDN make it easier because it's a more limited domain, or does it actually make it harder because it's got a whole different set of constraints?
Right. Yeah, that's a great question. That's great. I mean, like I was listening to Nick McCune's interview with you, and he talked about how they wanted to bring software into the network. And as somebody who used to wrestle with trying to deal with networking and verification, 10 years ago, back when all you had was this language that some company owned, and you didn't entirely know what it did. We had a grad student go off on eBay and buy a Cisco router and throw packets at it to try to understand what it does. I mean, we've all been there, right? So from one point of view, the great thing is we brought software into the network. The worst part of it is we brought software into the network, right? We know a lot about software, but we also know a lot about what goes wrong. So it is absolutely the case that it's now fantastic that we have some control over what's going on, which when it's no longer in some proprietary space, we can throw tools like testing tools and verification tools at it. I worry a little bit that over time people will discover exactly how little these tools do often achieve, right? And some of that promise will be discovered to be like more pain than promise. And I think we'll see some sort of cyclic thing, right, where eventually people say, well, that was too hard, so now let's go create some domain-specific language that'll make it easier to test and easier to verify. And FlowLog is arguably one of those. And then then there'll be a backlash against that. So I think the usual sort of software cycle will play out. But it is the case that we know a lot more about testing and verification and so on. There's great stuff like this wonderful project called concolic testing, right, which is combining symbolic and concrete testing and so on. All of these things are now techniques that were not there 10, 15 years ago that we can now bring to bear. So there's a lot of innovation in the software world, a lot of innovation in the networking world, and SDN definitely provides a place for both of those to stand together. And we'll discover, like from a verification perspective, there are going to be things that will simply not work because the network is a different thing than a program running on an operating system, a traditional operating system, right? Where to get good decidability, we're going to have to figure out how to encode a theory of the network, a theory of, and we've done some of this, of course, theory of IP packets, a theory of this, theory of that. But once we do that, we'll discover that now we can bring all this other cool stuff to bear and good things will happen. So I think the right thing is to be cautiously optimistic. I'm a little cautious because some of the stuff that never works quite as well as we'd like, but I'm definitely optimistic because there's a lot of stuff there to work with.
One thing that I wanted to ask you about too that we haven't quite touched on really is like just this area of software testing. I mean, this came up a little bit like even this week, like some stuff we built on top of Pyretic. Pyretic has a regression test. They made some changes to the way packets were handled, and then all of a sudden our app broke.
Yeah.
Like, oops. Didn't have the right set of regression tests, but it seems to me like okay, now we are into this world of sort of like regression testing and just also just testing in general.
Yep.
What's kind of the state of affairs, or kind of the sort of I guess your sort of general opinion on software testing versus formal verification, and specifically as it applies to like SDNs? I mean, it seems like certainly like anyone who's looking at verification right now, maybe because of the people who are working on it, I don't know, but like are really taking more of sort of a formal verification approach more than like a testing approach. So what's your thought on that?
Right. So I think we now know a lot more about testing than we did 15 years ago. It used to be that 15 years ago, I mean, obviously there were always people doing sophisticated things, but there was a lot of emphasis on thinking about different notions of coverage and so on. And that was good. That was important. It laid a good foundation. But now we have much more integration of the sort of formal. If you want to think of formal verification and testing as sort of two different camps, there's a much better understanding of how these two camps come together. There are concrete activities, like I said, concolic testing is one. There's a lot more use now of writing specifications and generating tests from specifications. This is an old idea, but it's made a serious revival in many ways. And how do we do this kind of random exploration to the search space and make it better and so on? We're doing a lot better job at this than we used to before. Yeah, obviously, like with everything else, having really powerful computers, SAT solvers, and these cool AI tools and machine learning and so on, all of this really helps because we have great data structures, great representations, good optimization techniques, all of which are good because we're searching through a space, and anything that makes representing spaces and searching through them better is good for us. So I don't think of these things as at all being in conflict. I think you're right. I think there's been some, to some extent, maybe I'm a little guilty of this too, there's been some extent like the formal stuff has been emphasized more than the testing-oriented approaches. That may partly reflect the fact that the formal stuff and I may be maybe a little mistaken on this, but tends to go with people who are building languages, and so they have more control over what's going on. In the software space, there's so much churn, and there's so many different frameworks, and they're all kind of halfway there, and they're all still building up, that investing in putting a lot of effort into testing one of them, if you're not one of the creators of them, it's just not clear that that's where you want to put emphasis in just yet. Right? So there may be a little bit of that, and once there's like more clear winners in this framework space, then people who do testing might come in. But I want to actually talk about one thing that's really related, which I alluded to, which is what this thing that we've been doing that we call change impact, right? Which is verification is great when you have a property you want to verify. Right? I've got something and I want this thing to be true, but oftentimes that's not the real life of a programmer or of a developer, right? We've got a system that we have confidence in for some reason, sort of works for some reason, right? Whatever reason we believe it works, it works. And then we change it, and now, and we've had this conversation a lot with NetOps, and I'm sure you have too, where you say like, okay, what is your standard technique when you change this thing and you want to know does it still work? And invariably the answer is some variant of pray, right? So can we do better than that? So I'm really interested in this question of, so this is a kind of property-free world, right? The property is how much is it the same, right? That's one kind of property. And so can we bring all this machinery of formal methods, all this representations and search space techniques and so on, to bear on this question of differencing? And that's actually where we put most of our effort now in FlowLog, and we did in this Margaret project as well, because that's something that a developer, an operator, completely understands the problem, right? If I say, well, I've got this tool, and you first have to learn temporal logic, it's like, well, thank you, and I'll get back to it in a year, whereas this is a problem they immediately understand. So we're putting a lot of effort into that, and I think that's another place that's bridging the sort of testing-oriented view. In fact, that's exactly what you said, right? It's a regression question. And I made this mistake before. Do I still have this mistake? I don't know what
property it is that I want to express. I just know that it seems to work now, and I'd like it to continue.
I'd like that to continue. Exactly. And this actually goes back. I mean, there's like good human psychology reasons also to be thinking about this, right? We're really bad about thinking about the things we don't think about, right? It sounds like a truism, but there's actually some content to that statement, like unknown unknowns, whatever. Right? And so being able to say, hey, did you realize this was going to happen? And so this is the other thing, is you have to think of this as an interactive process, right? You get some output and it says, here's lots of things that might have changed. And you say, well, okay, don't tell me about those things because I expected those. Now tell me about the things, you want to apply a filter to it, you want to apply a view on it, right? Tell me only the things that affect my egress filters because the rest I don't really care about. And then like, oh, that kind of packet is now going out. Well, I didn't want that to happen. Right? So we have to create opportunities for people to be surprised, because the surprises are the ones that get them to reflect. And the really funny thing is, then people start to build up properties. They're like, you know what? I never really want that to happen. So now I'm going to state that as a property, and that's a kind of way of trying to bootstrap the verification process as well, rather than just saying, here's a tool, and if you don't have any properties, it sits there and does nothing. Right? So that's another way, another approach to trying to bring the sort of the informal but coverage-based testing world with the formal property world.
That's interesting. Yeah, I guess another thing that I mean, probably can be highly frustrating for a programmer or an operator is like, you run a formal verification tool and it's like, okay, that property failed.
Yeah.
Okay, so now tell me how I fix it. And even worse, like with the data plane, right? Like maybe the control plane's fine, and like, okay, I have a loop or a black hole. Okay, tell me how I got into this state. Like,
that's right.
What sequence of events led me here, and
that's right.
Tell me what part of my control logic is messed up that got me into this state. Like, do you think that, like, I mean, the stuff that you're working on, or other things, like, in general, does verification help troubleshooting, or is it a related set of tools? I mean, where are we in the state of troubleshooting here, and what kind of problems, are solvable, should be solved?
Yeah, that's a great question. Yeah, I think these tools have a lot of potential, but one thing is also you have to think about even when the tool has the information, I think you've got to put a lot of effort and think about how to present that information, which, I mean, sounds kind of obvious. It's unsurprising you have to put that effort in. Like in FlowLog, for example, we have taken as a founding principle that people prefer concrete examples. So even though we construct this mathematical object that represents all the possible things that can go wrong, what we do is actually we just spit out concrete examples, instances of it, and then people can say, oh, show me an instance of this form, and then do a guarded exploration of the set of instances, and that's a way of understanding. That's a model. That's a belief we have about users, and there's some user studies and stuff that some people have done that suggest that
I
they
think
think
that
that
way.
way.
Yeah, I'm not a mathematician, so I appreciate that a lot.
Yeah. Well, you're pretty good at faking not being a mathematician. Let's put it that way. But it is the case that even mathematicians, right, work with concrete examples. That's what they do, right? They don't prove a theorem. They go to the board, they draw an instance, and say, "Nah, what about that? That should probably be over there." And like, yeah, you're right. And then that's how they generalize, right? They go from it's induction, right? It's Baconian induction is what it is. So we think giving people concrete examples, but then sometimes the examples can also be overwhelming. It's like, oh my God, it's like, is there a more general structure? You're telling me that there are 1,000 little examples, but there must be some more general structure. So then how do you help for somebody to say, oh, tell you what, I can generalize this part of this, I can generalize that part? I think there's actually a huge opportunity for HCI research here. Right? There's been a little bit of work on understanding admins. Some of it is anecdotal, some of it is more rigorous. But I think there's a huge opportunity if we can understand what a typical admin, or maybe 2 or 3 kinds of admins, what their affordances are, what kind of models, presentations work well for them, and then build our tools to cater to that. That would be so awesome.
Yeah, no, absolutely. I don't know, actually, another thing that certainly people have asked us, and maybe this hits like right on your HCI point, is that, we designed this, we're like, we think this is kind of easier to manage or easier to check. And then
Right.
Without actually trying it out, right? So,
Yep.
you tend to be like, well, how do you know? Like, I mean, how do you know that this is the right way to do it? I mean, is that something that you face as well, like in terms of like designing these systems? Is that something that you have to worry about? Are those comments that you say get from reviewers or
Well,
other
less
things?
so reviewers. I think reviewers are kind of like us, so they're willing to believe these things a little more. But no, I mean, I think reviewers it would be good for everyone, all of us, to be more skeptical about these things. And certainly, I mean, I've read some of the HCI literature. I've done a little bit of non-network related HCI, and it's something I would love to do more of, but I'm just utterly unqualified, so I just sort of bumble around in the space. But it would be really neat if more people and more HCI people, and of course I know you've been involved in some of these projects as well, more of the sort of HCI networking interaction took place, and we could do more to really understand what makes sense for these operators, because they're really precious resources, right? Every minute an operator wastes, we can measure in dollars, and pick your favorite unit of currency. So we can really measure these, and so I think we would all benefit from being a bit more skeptical, not at the point of like cutting off research and saying no, don't do that. But at some point there's got to be that transition as well. It's like a different kind of technology transfer.
No, absolutely. Yeah, I guess that actually kind of taps on my last question, which was, what do you think are, let's say you've got a grad student walking in the door, or anybody for that matter, who wants to work on verification. It's, what would you have them focus on? What are the most important problems? I mean, you just touched on a really important one, which is sort of like, how do you basically design an interface or affordances to network operators, because they don't want to write down math or these types of things. And then I think we talked about some other things like, security being a challenge. I think another thing that you mentioned was sort of coupling these temporal logics with state-based logics. I mean, a lot of interesting things that I think came up. But anything else? Like?
No, I think that's a great list. I mean, I think the thing that's really cool about the list you just gave me is it just shows how diverse this area is, right? I could give a problem depending on the student who came in. If they're an HCI-oriented student, I can give them a hard HCI problem. If they're a theory-oriented student, there's some hard theory questions. If they're a PL student, there are hard PL questions. And every one of those areas makes progress, right? Progress in one area helps all the other areas. At least it doesn't hurt the other area, and maybe defines the area problem for that area a little bit better. And that's what's just so awesome about working in this field, is like every one of these things. And there's also the software engineering questions like testing and so on. And and the interplay between these, right? Like, how does the HCI make it might even change the verification problem we work on. The verification changes the testing questions we need to ask. And it's just this beautiful interlinked area, and that's what's so great about it.
Yeah, no, lots of cool stuff. It's gotten me very excited as well. I sort of thought the whole thing was dead like 10 years ago, as you pointed out, like when we were buying Cisco routers on eBay.
Yep.
But it's kind of like a whole new world now, so it's
It
cool.
totally is.
Um,
Totally.
yeah. Well, thanks a lot. Thanks for your time.
Real pleasure. Thanks. Great talking to you, Nick. Bye-bye.
Okay.